Hi, my physics students. Welcome to another fun flip video with Mr. Bozade. Today we're going to be looking at how we can apply some of our mathematical models to objects that are orbiting. We've been doing a lot of work lately with the International Space Station, and we've been talking about it a lot. So I thought that would be a good example for us to apply our mathematical models to and try and calculate some kind of factors or variables about the International Space Station. I think you're going to be pretty impressed with some of the things that our International Space Station does as it orbits the Earth. I've got all real values here. That's the radius of the Earth. That's the altitude that the International Space Station is above the surface of the Earth. That's the mass of the Earth, and that is the mass of the International Space Station. The goal that I thought we would try to achieve here is to find the period of the International Space Station. Before we dive into plugging numbers in, I thought it would be a good idea for us to kind of think through how we're going to eventually reach that goal of finding the period of the International Space Station. So let's think about that. We know when something moves in a circle that's orbiting, it's going at a constant speed. And we know that that speed or velocity is equal to the distance over time or the circumference because it's moving in a circle over time. And we know that circumference is 2 pi r. And when I say over time, I really mean over the period, right? Because what we are doing is we're doing the distance it takes to travel once around, and then we divide it by the time it takes to travel once around. And the time it takes an object to travel once around its orbit or once around the circle is called the period. So if we look at this, I think we can find that radius, because that radius is the radius of the orbital circle, which would be from here to here, all the way from the the edge of the orbit to the middle of the circle, which is the center of Earth. And we have those two values, right? We've got the altitude of the International Space Station and the radius of Earth. So we have those two things, so we can add them together. Let's go ahead and do that, because we know we're going to need that value. Before we do anything, we need to put this into meters. So the radius of the Earth is 6.378 times 10 to the third kilometers. To put that into meters, we need to multiply it by 1,000. So we can change that from 10 to the third, we can change it to 10 to the sixth, and then it's in meters. Likewise, the altitude of the International Space Station is 4,000 kilometers. Let's multiply that by 1,000. So we'll make it times 10 to the third, and now it's in meters. If we add those two things together, we'll get the radius of the orbital circle, and that's going to be 6.778 times 10 to the sixth meters. So now we have that radius, the total distance from here to there. So if we look back at this equation, we've got radius. Period is our ultimate goal, right? That's what we're trying to find. But we don't have the speed that the International Space Station is traveling as it orbits the Earth. So let's see if we can find that speed using a different equation. Well, the equation we just derived today was centripetal acceleration equals velocity squared over radius. Okay, as we just said, we know the radius, and we need this velocity so we can find that speed, but we don't know the centripetal acceleration of the International Space Station as it orbits the Earth. Well, at this point, I think we can recognize that there's two ways we could find that centripetal acceleration. One way we could find it would be to find the gravitational field strength at that height. Because as we know, when something's in free fall, gravitational field strength equals acceleration. So we could find the acceleration because it's equal to the gravitational field strength, which is g, mass of the Earth, over the distance between their centers squared. Another way we could find that acceleration, the centripetal acceleration, is we can do net force radially equals mass times mass of the International Space Station times the acceleration of the International Space Station. And since we're adding up the forces radially, that's going to give us our centripetal acceleration. And the only force that's acting on it is the force of gravity. So what we're really saying is we would do g m1, mass of the International Space Station, times m2, mass of Earth, over r squared equals mass of the International Space Station times the centripetal acceleration. And I think in all these cases, either this case or this case, we could find acceleration, and we have those given values. G is a constant, we're given mass of Earth, and we know the radius. So using this method, we could find acceleration, find velocity, and then we could find the period. Over here, let's see, G is a constant, we know mass of the International Space Station, mass of Earth, radius, mass of the International Space Station, and again, we could find acceleration, find velocity, find speed, which gives us speed, and then we can find the period. So now that we've kind of thought through the process that we'll take, we just got to decide which method we want to go with. I'm going to do this one because it takes a little longer and it'll show you a little bit more of a few more extra steps in solving it. You certainly could have gone with that method, and as we can clearly see, mass of the International Space Station cancels out, which is why it makes sense when something's in free fall, the acceleration experiences is equal to the gravitational field strength. All right, so if we're going to start with this, then we're going to say net force equals ma. Let's scooch this over so we can see. So we will start with net force centripetally equals mass times centripetal acceleration. So the net force is force gravity, and it's going to equal mass of the International Space Station times the centripetal acceleration. Force gravity is going to be G, mass of the International Space Station, times mass of Earth, divided by the distance between their centers squared, which equals mass of the International Space Station times acceleration, centripetal acceleration. Like I said, we've got mass of the International Space Station right here, we've got mass of the Earth right there, and we've got this distance between their centers right here. So you plug in all those values, and you find that the force gravity on the International Space Station is 3,643,000 newtons. So that's going to equal mass of the International Space Station times the centripetal acceleration. We divide mass of the International Space Station over, we find that the acceleration is 8.68 meters per second squared. So that is the centripetal acceleration that the International Space Station is experiencing as it orbits the Earth. And like I said, that is also going to be the gravitational field strength. So we could have also said 8.68 newtons per kilogram is the gravitational field strength at that distance away from the Earth. Because when an object's in free fall, the acceleration that it experiences is going to be equal to the gravitational field strength that it is also experiencing. Another interesting fact that we could notice is that since mass did or would cancel out, this is also the acceleration that an astronaut like Sunny Williams might feel in the International Space Station, because we could have put her mass in there and it would have canceled out. And that makes sense also because the mass of the object doesn't matter when we find the gravitational field strength. The gravitational field strength at that distance away from the Earth is this value no matter what the mass of the object is. So an astronaut or the International Space Station feels the exact same gravitational field strength at that altitude. All right, great. So now let's come back here. Now that we've got acceleration, let's find our velocity. So our new equation for centripetal acceleration is that it's equal to v squared over r. And we've got our acceleration now, so we can say 8.68 equals velocity squared, that's what we're trying to find, over r. And this is the radius of the circle. That's the radius of a circle, because this is talking about an object moving in a circle, and so the radius of the circle is not the radius of Earth, not the height above Earth, it's this distance here, because that is the circle of orbit. So we put in 6.778 times 10 to the 6th. So I'm going to put that in there. 6.778 times 10 to the 6th. Multiply that to the other side, square root, and you will find that the velocity of the International Space Station is, I have it written down here, 7,670 meters per second. 7,670 meters per second is the velocity or the speed of the International Space Station. That is amazing. That is so cool that our International Space Station is going that fast. 1 meter is about this big right here. So imagine 7,670 of those lined up, end to end to end. 7,670. The International Space Station goes past that many in 1 second. 7,670 meters in 1 second. That's how fast the International Space Station is going. And again, we've used all completely real values, and this is completely true. That's how fast the International Space Station is going. Wow, so if it's going that fast, then I wonder how much time it takes to get around the Earth. Let's find out. Well, now that we've got our speed or our velocity, we can now find the period. Because we know that speed is equal to 2 pi r, the distance, which is the circumference of the orbit, divided by the period. Let's see, so we've got our speed, 7,670 meters per second, times 2 pi times r. And again, this is the radius of the circle of motion. Well, this is the circle of motion, so we need to use that 6.778 times 10 to the 6 meters over period. And then we can solve for the period. Multiply period to the other side, divide by 7,670, and you will find that the time it takes for the International Space Station to orbit around the Earth is 5,552. So 5,552 is the period of the International Space Station's orbit. But what, wait, Mr. Bozade, 5,552 what? 5,552 seconds. That's how much time it takes the International Space Station to orbit the Earth. But that's not really a very useful value because, like, let's say that you called up your friend said, hey, I'm coming over, and you said, hey, how soon are you going to get here? And they said, well, I'll be there in about 5,562 seconds. You'd say, is that soon or late? How soon are you going to be here? We need to convert that to a useful value. So let's divide that by 60 and see how many minutes that is. Turns out that is 92.5 minutes is the period. That is 1.5 hours. The period of the International Space Station is just over 1.5 hours. That is amazing. That is remarkable that the International Space Station orbits around the Earth in 1.5 hours. That means that 16. That means the International Space Station gets around the Earth about 16 times every single day. That's incredible how fast it goes. No wonder when I look up in the sky and I find it, it's able to traverse my entire viewpoint in 4 minutes. It goes from the one horizon to the other horizon in 4 minutes because it's going so fast. It's amazing. Cool. I hope this was helpful. See you later.